Hi Chem Phys students, Mr. Ragusa here. We're looking at our Unit 7 Energy Study Guide. We're going to go through a couple questions here. The first one asks, what's thermal energy? Thermal energy is energy that's stored due to the motion of moving particles. So in this idea of stored moving particles, particles that are moving fast have lots of thermal energy, and particles that move slow are not. That's kind of like our kinetic energy from physics. Now when we go to what is phase energy, that's stored energy due to the particles' arrangement. And what we mean by arrangement is whether it's a solid, a liquid, or a gas, and how those particles are spaced out and how those particles move around. So the most phase energy would be a gas, the second most would be liquids, and then solids have the least amount of phase energy. So next it asks us to describe what happens to particles of a sample of water when it's heated. Well, when a sample of water is heated, the particles begin to move faster. The amount of thermal energy goes up. Now eventually, if we heat it up enough, we'll eventually have it start changing from liquid water to water vapor, which we call steam. So eventually we won't be able to get it to heat up and do that. So over here we have two samples of water. One is hot water, one is cold water. And what I would label is that the hot water is over on this side and the cold water is over on this side. So for each of the following, either choose hot water or cold water and explain why. Which particles are moving faster? Well, the reason we chose this one is it has more of the little motion lines. So the hot water does, because according to temperature, since it has a higher temperature, that means it has more thermal energy. Which one has more thermal energy? Well, I guess we already answered that one, the hot one. Why? The higher the temperature, the more thermal energy. Which one has more phase energy? Since they're both liquids, I would say that they are the same. Why? Because they're both liquids. Now, even with water particles, there is the ever so slightest amount of the particles are spaced out further when they're hot than when they're cold, but not enough to really affect phase energy. For total amount of energy, I would say that the hot sample has more energy. Why? Well, if we were looking at the energy bar charts, they both have the same amount of phase energy, but because these particles are moving faster, you have more thermal energy. Alright, next it asks us to identify what's happening in each region of the graph on the right. So region A, we are heating a solid. In region B, we are melting. And I'm, of course, assuming that the energy is going this way, so that time's going that way. During part C, we're heating a liquid. At part D, we are evaporating. And then at part E, we're heating a gas. Okay, so now it asks us a couple more questions. At what temperature does this substance freeze? Well, it freezes right here where this plateau or V is. So that looks like it's approximately 5 degrees Celsius. And then where does it boil at would be right here, where D is. Looks like it's about 15 degrees Celsius. Now, the melting point is going to be the same as the freezing point, so that would be 5 degrees. And then the condensation point is the same as the boiling point. It just matters whether you're going to the left here or whether you're going to the right here, depending on if you're going from a solid to the liquid or from the liquid to the solid. Question 8, if the substance is absorbing energy in regions B and D of the graph, why isn't the temperature going up? Well, at region B, we're changing phase. So the energy is going into the phase account. Is the phase energy increasing in regions B and D? Why or why not? Yes. At B, it's changing from a solid to a liquid, and at D, it's changing from a liquid to a gas. So at those regions, we're going through a phase change. And when the phase changes, we're going to have basically a change in that phase energy. Looking on to the next page. Why doesn't the temperature of a substance change while it's melting? Well, the energy isn't going into the thermal account. It's going into changing the arrangement of those particles. What is the law of conservation of energy? How can we see this in action when the substance is heated or cooled? So the law of conservation of energy states that energy cannot be created or destroyed, only transferred. So how can we see this law in action when a substance is heated or cooled? So whenever we have an energy transfer happen, things always flow from hot things to cold things. But when they do this, they always transfer energy, such in a case where the amount of energy that goes from the hot thing that goes to the cold thing is equal. So you can't get more energy to flow from the hot thing to the cold thing than you left from the hot. So those two amounts of energy always have to be the same. What does endothermic mean? Endothermic means a process where energy is absorbed. So a couple examples I can think of. If I have an ice cube, and I put an ice cube into any kind of drink, that ice cube is going to be absorbing energy from whatever the other drink is. So this process for an ice cube of gaining heat is endothermic. Another really good example would be something like a hot, or rather a cold pack. So in a cold pack, there's a chemical reaction where we break these two chemicals. They mix together, and a chemical reaction happens that absorbs energy from around you, and because you're losing energy, that feels cold to you. So that's the reason that we think it's cold. I think of endo, the key part of that I think is enter. So heat is entering into the system. We contrast that with exothermic. Exit is kind of what I think of, and it's a process where heat is, instead of absorbed is exiting your system. So, like, what are a couple examples of that? Well, in the last example with the ice cube, if we have an ice cube, the thing that the ice cube is around is losing energy to the ice cube. So, like the soft drink that you put the ice cube into, that thing is losing energy in that process. Likewise, we also create, kind of similar to a cold pack, we create like hot hands or like a warm pack. And those warm packs have a chemical reaction that happens where like energy comes out of chemical energy in those bonds, and that basically is going to go to whatever is around it. So if you're holding on to that chemical reaction, that pack, that heat that's exiting from the chemical energy is going to enter you as thermal energy. So the next question says that a piece of metal is heated and submerged in cold water. Describe what happens to the particles and the energy of the water and the metal. So the water is going to gain energy and the metal is going to lose energy. And the amount of energy that the water gains will be equal to the energy that the metal loses. And in that process, the water is going to heat up, meaning that the temperature goes up. So that means the particles are going to move faster. And the metal is going to cool, meaning that the temperature will go down, which means the particles will move slower. Room temperature water is placed in a pan and boiled away entirely. So if we had room temperature water, first of all, water is a liquid, so I would say that my phase energy would get 2 bars. And the reason I'm going to say 2 bars is we said that whenever you have a liquid, you always have 2 bars of energy. So now for the thermal energy, room temperature, we normally give just 2 bars of energy to. Now, if we're going to take this water and we're going to boil it away, that means that first of all I'm going to need to increase the temperature so that way we get to the boiling point. And second of all, when it's boiled away, it's a gas, and we give gases 4 bars of phase energy. So that means that the difference between my initial conditions and my final conditions is the sum of 4 bars different. 2 in the thermal and 2 in the phase. So here for my energy flow, I'm going to show energy going into that system. I'm going to have 4 bars of energy going in. That means that since energy is going into the water, this is an endothermic process. Energy is going to be going up. Water vapor in the room condenses on a cold surface, assuming no temperature change. So for this one, we have, starts off as water vapor, which is a gas. So because it's a gas, we have to give it 4 bars of energy. The amount of thermal energy we start with doesn't really matter because we think that one is going to stay the same. I'm just going to say that it's like room temperature water. The problem says assume no temperature change. That means my thermal count stays the same. Now, if I condense, that is specifically the phase change where I go from a gas to a liquid. So to go from a gas to a liquid, I would go from 4 bars of phase energy to 2, which means that 2 bars of energy are going to exit my system. Since heat is going out, that means this is an exothermic process. Alright, next we have a cold spoon that's placed into a cup of hot coffee. Draw an energy bar chart from the perspective of the coffee. So the coffee starts off as hot. So I'm going to give it 4 bars of thermal energy. And since it's liquid, I'm going to give it 2 bars of phase energy. Now, afterwards, the coffee is going to cool down, but it's not going to cool down like to a solid. So it's going to stay a liquid, but I'm going to say maybe draw 1 less thermal energy bar, showing that the energy went down. So the coffee is losing that bar of energy. For the coffee, that's an exothermic process. Now, from the perspective of the spoon, well, the spoon, first of all, is a solid, so it's going to have 1 bar of phase energy, and it's not going to melt. But initially we say that it starts off cold, so I'm going to give it 1 bar of thermal energy, and then afterwards, because the coffee lost 1 bar of energy, that means the spoon is going to be gaining a bar of energy. And that bar of energy is going to go onto the thermal account. So now it's going to have 2 bars of thermal energy at the end. So it's an endothermic process. The spoon is absorbing energy. What is specific heat capacity? Specific heat capacity is defined as the amount of energy to raise 1 gram of a substance by 1 degree Celsius. The specific heat capacity of 1 gram of aluminum is 0.9. What would the specific heat of 2 grams of aluminum be? Specific heat capacity is a property of matter. So what that means is it doesn't matter how much aluminum you have, the specific heat is always going to be the same. So if I had 1 gram, it would be 0.9. If I had 2 grams, it would be 0.9. If I had 100 grams, it would still be 0.9. So it doesn't matter how much of it I have, as the specific heat capacity of a substance is not going to change based off of how much. Next, a piece of copper and a piece of iron have the same mass and are heated the same amount of energy. Which one will have the greatest rise in temperature? Well, in taking a look at my chart here, copper takes 0.39 joules of energy to raise 1 gram of it by 1 degree. And if I have 1 gram of iron, it would take 0.45 joules of energy to raise it 1 degree. So if I have equal size pieces, say that I had 1 gram of each, they're heated with the same amount of energy. That means that the copper will raise more degrees of its temperature. And the reason why is because each degree to go up, it takes less energy than iron. So things that have really high specific heat capacities take a lot of energy to change their temperatures. Things with really low specific heat capacities, not as much. Identify 3 factors that determine the amount of heat transferred to an object. So when I'm trying to figure out heat transferred to an object, we're talking about Q. And the factors that are going to affect that are going to be M for mass, which basically is like how much of your substance are you increasing the temperature of. C is the specific heat capacity, which is that thing that we had just defined. And then finally, delta T, which is change in temperature. Obviously, when we talk about specific heat, it's for 1 degree Celsius, but say that we wanted to move 10 degrees Celsius instead of 1, how much that temperature changes is going to impact how much energy is required. Okay, so the following day was gathered during a lab in which a peanut was burned underneath a can of water. So for my data, first thing we have is the mass of the water heated. So we have 100 grams of water that's basically kind of like on top of a peanut that's being burned. The mass of the peanut burned is 2 grams. The initial water temperature is 25 degrees Celsius and the final water temperature is 30 degrees Celsius. So if I wanted to calculate heat absorbed, we're calculating Q. In my equation, Q equals M times C times change in temperature. So my givens that I need to come up with are M, C, and change in temperature. Now the mass is the hard part. There's 2 masses here. My initial temperature is 25, my final temperature is 30, so that means my change in temperature is going to be 5 degrees. Well, that 5 degrees is the change in temperature of water. So the mass I'm going to use is going to be specifically the mass of water. So that's 100 grams. And the specific heat I'm going to use is not the specific heat of a peanut, it's going to be the specific heat of water. It is 4.18 joules per gram degrees Celsius. So when I substitute my values in, Q is going to be equal to 100 grams times 4.18, and this means not specific heat, or joules per gram degrees Celsius, times 5 degrees Celsius, which would give me an overall energy of 2,090 joules. Alright, we're down to our last page, which is going to be some specific heat calculations. Now the topic gives us the specific heat of solid ice and the specific heat of liquid water. So first it tells us a sample of water, so it means that the specific heat value that I'm going to use is going to be 4.18 joules per gram degree Celsius, is heated from 5 to 30 degrees. Well, my change in temperature from the end here, 5 to 30, infers that my temperature went up by 25 degrees Celsius. And then finally the mass, it tells us, is 20 grams. Wants us to calculate energy, so we're going to use the MCAT equation. When I call it MCAT because the delta T kind of looks like an A. So to substitute my numbers in, Q is equal to 20 times 4.18 times 25, which would give me an energy amount of 2,090 joules. We got there a little bit of a different way than we had last time. If 130 joules of energy is absorbed by a sample of ice, that means the specific heat I'm going to use is going to be 2.11. Is heated from negative 20 to 0, solve for mass. So this time it wants me to find mass. From negative 20 to 0, that means that the temperature went up by 20 degrees. And I have 130 joules of energy, so that's my Q. So now here we want to find mass. My equation is the same to start, but if I wanted to rearrange it and get M all by itself, I would need to divide by M and delta T. And so I'd have Q divided by C and delta T is equal to M. So I'm going to use that rearranged equation, and I would get 130 joules divided by the specific heat of 2.11 joules per gram degree Celsius and 20 degrees. So just be careful when you put this into your calculator that you might have to put a parenthesis around this, or just do them kind of one at a time. But you would end up getting a value of 3.08 grams of ice. Next question. If 200 grams of lead, so that's my mass, is heated from 10 to 60 degrees Celsius, so that means my change in temperature is 50 degrees. It has a specific heat of 0.13. So that's my C. How much energy is absorbed in that process? So it's going to be Q equals MC change in T Q is 200 grams times 0.13 is my specific heat times 50 degrees. This would give me a Q of 1300 joules. Alright, we're getting down to the end. We got 2 questions left. Scrolled too far. This one says that a pot is 350 grams and it's room temperature water. So my mass, 350 grams, and I have room temperature water on a stove and it's being boiled. When the water reaches 100 degrees, how much energy has been absorbed? So my change in temperature, we went from 25 to 100 degrees. So that's a change in temperature by 75 degrees. And then since I'm liquid water, during that range of temperatures, remember that water boils at 100 and freezes at 0, it means that I have liquid water 4.18 joules per gram degree Celsius. And it's asking me to solve for how much energy was absorbed. So my equation, Q is equal to MC change in T. So Q is 350 grams times 4.18 joules per gram degree Celsius times 75 degrees. This one's going to be a lot more energy, and it gives us an amount of energy that is 109,000, sorry. 109,725 joules. The last question on the assignment says that a welder needs to craft a copper pipe for the plumbing in a home. He takes a 500 gram sample, so my mass is 500 grams, and he heats it with 4,000 joules of energy, so that's a Q. We know the specific heat of copper is 0.385, so that's my specific heat, 0.385 joules per gram degree Celsius. How much did the temperature change? So it wants to know delta T. So my original equation is Q equals MC change in T. If I want to get change in T all by itself, I would need to divide Q by M and C. So Q divided by M and C is equal to change in temperature. So to substitute in my values, change in T is equal to 4,000 divided by my mass of 500 grams times the specific heat capacity, which is 0.385 joules per gram degree Celsius. So you put those together and you would solve for the delta T, and you would calculate that the temperature would change by approximately 20.78 degrees Celsius. Thanks for watching. Hopefully this is a useful video, and good luck studying for the rest of your test.